In the last lecture, we saw the derivation of Bohr's theory and various tweaks that is possible within the Bohr's theory. And one which was very important was the reduced mass system, like when the nucleus is also been assumed to be moving in a circle instead of being at rest. And the moment this happens, the rule says that you have to remove the Rydberg constant. R infinity is called the Rydberg constant, and Rmu you can say is the reduced Rydberg constant, and the value is simply mu by mass of electron. So this formula will change the relationship between the old formula which you know from with respect to the new formula that we can have. So this is the important conversion factor in particularly Bohr's theory. We also saw in Bohr's theory that how we actually derive the relationship between the d wavelength, that is lambda, with the confinement space dimension. So like we had a orbit as a confinement, and we say that okay, the number of wavelengths or the number of standing wave, basically, so you can see the number of standing wave in each half perimeter. So this is like a node, and we know between two successive nodes, the separation will take as lambda by 2. So we can say that n lambda by 2 was equals to pi r, and therefore n lambda becomes 2 pi r, and then we replace the lambda by the h by p, the relation, the momentum relation, and so you got the pr equals to h by 2 pi as the Bohr's quantization rule. So basically, the Bohr's quantization rule was the consequence of formation of standing wave that we assume that is being formed by virtue of uh, the reflection of electron cloud with itself. So these are just models, and I have told you that these models are someone's imagination about the world which is within that. And these models are accepted because the moment we assume this model to be true, certain phenomena that we have encountered in practice can be explained or justified. So these are the reason for the acceptance of model. But of course, these models were like the very preliminary stage model, and therefore nowadays these are totally rejected. But it paved the way for the further development into the quantum world. And there's a beautiful history that how came to know about this. And I believe that I have shared that history, right? Like he was working with the light, and he got the H spectrum called the absorption spectrum, and he found some missing lines, and these missing lines correspond to the absorption of photons in the certain band of energy, and therefore we can say the atoms are capable of only either releasing or absorbing energy in the discrete values. Not all values can be absorbed or released during a transition from one orbit to another. So what is most important to understand is that in case of Bohr's theory, we have the concept of energy levels, and these energy levels are of fixed values. Every orbit represents one energy level, and that's why these having fixed value or stationary values. And because of this, the word stationary, I mean, we got the idea of stationary orbits. So the stationary orbits is like The electron can reside only in those orbitals where the energy of the orbiting electron is constant, which is exactly against the classical theory, which say that due to the circular motion of electron, it will undergo radiation, and by virtue of radiation, energy will be released. Okay. Later on, I will tell you that okay, the charge, something like charge. So I hope you have heard about this charge. So charge can be in three possible state, and how the classical physics look at the charge. So a charge at rest creates electrostatic field. When the charge is in uniform motion, it creates magnetic field. And when the charge is accelerating, it creates EM wave. That's how the EM waves are generated. So any accelerating charge creates a wave. And if you remember the concept of antenna, if you have seen antenna, okay, probably not, but if you have seen in either in movies or somewhere, so the antenna works on the very principle of oscillation of charge because the EM wave is nothing but the oscillating electric field and magnetic field. So let's say there's a very famous old antenna you might have seen somewhere in the like this. Have you seen something like this? This is pretty neat. So this is the old antenna, and the antennas in India, if you see, are I mean, it used to be mostly horizontal. Just a minute. Sorry, guys. If you go to Western world, their antennas are vertical. So there's a difference between the most of the Southeast Asia and the Western. And there's a concept of called polarization. So if you might have heard about the polarization in wave, that the light is called polarized if it can oscillate only in one plane. So if the light will oscillate in only one plane, this is electric field, this is magnetic field. Such light is called polarized light because the electric field will oscillate in one fixed plane. So we say plane polarized light, PPL. Okay. So as per the protocol of transmission in India, the waves are transmitting horizontally. So the polarization is horizontal, and these are like interceptors. So these antennas are like interceptors. So they intercept the wave which is horizontally polarized. So in Western world, they have the vertical polarized. So depending on like not maybe not like this, maybe they have something like this, but possible. So because of the kind of polarization, they have the orientation, and this is also very important. You need to know that the polarization and the orientation of antennas are very important. Then only it can intercept. And these are electric field actually. So when you say electromagnetic wave, then it will have the electric and magnetic field oscillating. Okay, I'm not showing the magnetic part, but you can. So what happens that every metal will have the free electron. So these are made of aluminum or any conductor. And the moment the radiation will hit it, they oscillate the free electron, and it is like a signal uh, to the device connected. So this is how the radar or the antenna works. Basically, antennas are nothing but the radar actually. So this antenna, which you see very often in available, is called the Yagi Uda antenna, or you can say radar. So it was used in the World War II actually, and after the World War II, this is now available for the civilization, and you will learn a lot about how the defense research of past year is given to society because they have the improved version of everything right now. So defense is always many steps ahead in terms of like latest development in the technology space, and the outskirted developments are given to the civilization for the consumption. Anyway, so the whole idea is the discreteness is a property of electron. So if electron is residing here, and if it wants to go here, then there is a quantum of energy it needs to be there. Now the quantum of energy needs to be there. Let's say the energy gap is some xev, something. Now the question is, if you give xev value of energy, electron volt is a unit of energy. So what is 1 electron volt? I hope you know. So 1 electron volt is equals to 1.6.
10
The
to minus
charge,
19 kg.
correct, joule. So it's a joule equivalent. So if you put the value of charge on electron into, as a joule, expressed as joule, this is called electron volt, which means basically if an electron is accelerated through the potential of V volt, then the energy gained by the electron will be EV. So if you learn the electron electrostatics, so we show work done equals to Q into delta V. So the charge will accelerate through the potential difference of delta V, then it will have the gain of energy this much or lose of energy this much, depending on whether you're going along the field, like accelerating or deaccelerating, depends. So these two orbitals will have a definite energy value to take the electron from here to here. Now, how this will be possible? So electrons are the part of the atom, and you cannot supply energy directly to atom. So what we do is we supply in terms of wave actually. So we supply some photons. So now these photons, if having exactly same difference value energy, so if h nu is what x ev, then electron will make this transition. So the question is, what will happen if the h nu is less than x ev? Will the electron will go to till here and will come back, or will not go at all? So what will happen? That's the question. Again, the question is, what happens if the h nu exceeds the x value, but not good enough to make another transition? So let's say if this one requires y ev, and or not this one. Let's say this transition requires y ev energy. So what will happen if the h nu is more than x, but somehow not good enough to be y? So how the atom will interact with the photon when energy value of the photon is something like this. This is what we need to explain today, and the topic is called our today's topic is called atomic collisions. And in this topic of atomic collision, what we will be studying here is the collision of atom with a photon, and then we'll study the collision of atom with another particle. So the first case we have to study is collision of atom with a photon. So definitely a photon. What is photon? So photon is a discrete packet of energy. So when I say a photon, then I talk about some finite energy value. So a photon will have the energy h nu. A photon will have the momentum h by lambda, and the lambda will be real. Of course, lambda is not d bro, it's the actual lambda because it's a wave. So when we have an atom, and if you assume the electron to be in any particular orbit, first, second, uh, so need not to be in the ground state, it could be in any state, first excited state or second or third or fourth. The rule is if the electron initial position of the orbit and the energy of photon, which is incoming energy, so we call it something called incoming energy. If the photon energy, which is being received by the atom, and you can say the electron of the atom, if this energy is equivalent of energy difference between any two orbits from the present state to any higher state, here or here or here or something like this, you can see it. Okay, so you can see that if the photon is coming, so if the electron can jump between any two orbits by virtue of the energy received by the photon, incoming photon. So if this energy value is exactly equals to any difference between any two orbits, so you can say 1 and 2, 1 and 3, 1 and 4, 1 and 5, and so on. Assuming that electron is in the first orbit, it could be in the second orbit, then 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and so on. It could be in the third orbit, then 3, 2, 3, 4, 3, 5, 3, 6, 3, 3, 8, something like that. If the energy of the incoming photon is equivalent of difference between the two orbits, in such case, the photon will be completely absorbed. Now, in physics, in atomic physics, when the when the atom completely absorbs the photon, such collision is called perfectly inelastic collision. So now the meaning of inelastic from the particle physics to the subatomic world of physics will change drastically. The definition will change. So here, even the photon, which is not a particle, which is like a wave, or you can say wave particle, or maybe some uh, conceptual particle. So when a photon will collide with the atom, then there are only two possible phenomena. Either we can completely absorb it and or do not absorb at all, because the partial absorption of photon is not possible. Okay. Now what does it mean? It means if the orbit in which the atom is electron is presently present, let's say electron is here. This is one and so on. So electron is here. Now if the incoming photon doesn't qualify, so let's say if the photon energy is even less than the nearest excitation value. So if it is less value, it cannot absorb. If it is slightly more than this value, again it cannot absorb. So the only rule it can be absorbed is when the difference between the two orbit and this photon is exactly same. When the difference will match, it will be absorbed. For any mismatch, it will be totally thrown back, and that's called the perfectly elastic collision. So let me tell you the meaning of perfectly. So there are only two possibilities: either perfectly elastic or perfectly inelastic. There is nothing in between. So there is nothing like partial absorption of photon. Photon cannot be absorbed partially. Only the difference between the two orbit and the photon energy. If it matches, then it will be absorbed, else not. Okay. So in case of collision of photon with atom, we have only two possibilities. One is perfectly elastic collision. So when the perfectly elastic collision will occur, when h nu is not equals to energy of excitation of electron. So when the energy of photon is not equals to energy of excitation. Now when I say excitation, it means it can go from the present orbit to any higher orbit. So I'm not mentioning which excitation state, first, second, third, fourth. But what I'm saying is that if the energy of excitation, which we need to make the transition for the electron, if that is not matching with the h nu, it will never be absorbed, and in such case we call perfectly elastic. So what is the perfectly inelastic? So when h nu is equals to delta E between present orbit to any other higher one. So if this is the case, then it is completely absorbed. In this case, photon will be completely absorbed. In this case, photon will be thrown back. Now, something that we need to be even more careful about is called the the conservation of momentum. So when we have collision, then in every collision, a momentum conservation will take place. But while solving numerical in JE context, the energy difference due to the momentum conservation is negligible, and therefore we assume that all of the photon energy is equivalent of the transition energy, and the kinetic energy requirement is very, very less. Now, what does it mean? So in every collision, principle of conservation of linear momentum will be followed. Okay. In every collision, principle of conservation of linear momentum will be followed. So let me show you the collision and the conservation principle, how it happens. So the ideal versus the real situation. So for the solving numerical, I'll assume that the electron is in the ground state. This is the H atom in ground state. Generally, question will be from the H atom only, and definitely they'll give you the ground state and other state. So now look at the question and how you can understand the question when solving. So let's say this is a photon with energy h nu, and whenever there is a energy, we have a momentum. So we say momentum is h by lambda. Okay. This is stationary atom. So these all hypothetical situations will be considered, and we'll proceed accordingly. Now, without saying, we'll assume these collisions are the head-on collision, but it could be oblique as well. And if the collision is oblique, things will change. Now, the photons are so small compared to the atom, then we assume it's a head-on collision. So it's not going anywhere else. So now the collision will occur. So as a result, let's think of the energy consumption. So what I'll assume for the sake of solving this question that the energy of photon is so A equals to h nu is basically equals to the first excitation energy. So let the incoming energy is equals to the energy of the first excitation state. It means the electron should absorb this energy and should go to this orbit. Do you realize this? What I'm saying? The meaning of first excitation energy. So the energy required to the minimum energy required to make the first transition is called the first excitation state. Understood? Am I audible, guys?
Yes.
But there is a flaw. So if I assume this energy is equivalent of this, so ideally it should not be absorbed. Why? The one component which we generally miss while solving questions like this is the momentum consumption. So look at the momentum part. So what is the initial momentum of system? So only photon is moving and the atom is at rest. So we can say the photon will have energy momentum h by lambda, whereas zero because the atom having let's say mass m is not moving at all. Now after this event, what will happen? So ideally, if photon is completely absorbed, let's say photon is absorbed. So the electron is now here in the first orbit, first excited state, second orbit. Now, if I assume this event happened, that H nu came, it is now being absorbed, and now we have this new atom in this particular state. So what we are violating here, if you assume this, because now you are saying the momentum is how much? Is zero, because the electron has gone into transition and the atom is at rest. So if we make this assumption, then what we are making a mistake? The mistake is we are violating the conservation of linear momentum. Do you realize this, the violation part? So we cannot assume the atom to be at rest. So it will have some velocity, but the whole idea is in reality, if the difference of energy, let's say this difference of energy, if exactly equals to this value, the transition will not occur because apart from transition energy, we need to give some energy as a part of conservation of momentum. So what does it mean is that this atom should have some velocity also, so that the initial momentum, we can avoid this and we can attach mv, and now we can equate the initial with 100. If we do not assume any velocity, then it will be like a complete violation. Okay. So if the atom starts moving of mass m with velocity v, how much kinetic energy it will have? Half mv square. Do you realize this? And if this is the case, then the energy of the incoming photon should be equal to how much? So the energy of, now we conserve the energy part. So energy of the incoming photon should be equals to the first excitation energy plus half mv square. Because the energy, if you want to conserve, then this is the only way to conserve. So do you realize this part? So generally, what happens that the momentum part. So if you try to, you can also write like the first excitation energy plus p square by 2m. And from conservation, this is the conservation of energy part. So we are conserving energy. Now from the conservation of linear momentum, we can write as h by lambda equals to mv. So basically, we can say this is p momentum part. So this you can see that from 1 and 2, from 1 and 2, what we can write? We can write h nu. The energy of the incoming photon should not just be equals to the energy of excitation, but rather it should have some more energy to maintain the conservation of momentum as well. And if it will not do, then things will be really messy. So, well, okay, let me substitute. Okay, I need to substitute here. So h nu equals to E1 plus h square by lambda square to 1. Fine. Let me write in terms of lambda. So Sc by lambda is E1 plus h square by 2m lambda square. So now the problem is the mass of atom is so high that this energy is almost nothing compared to this energy. So when you compare these two values, so technically Sc by lambda is on a greater side, but slightly on an equality. So this is roughly equal. So this is the reality, and this is the relation that we use for solving question. Use for solving. So the second term we actually do not consider, but now why I'm teaching this, the reason is in JEE Advanced, it is possible that they may bring some derivation like this, and you need to know that it's just a plain conservation of momentum and energy. So conserving energy in the world of atom is slightly tricky one, and you need to be very careful that we just cannot conserve energy. So what you need to remember is that we do solve the problem with the assumption that the absorption criteria is very much equivalent of h nu equals to energy of excitation. Okay. So let's say if I tell you what, if I tell you that mm, uh, if I tell you that a photon of energy 1.89 eV has been absorbed, so what you can infer? So let's say some H atom has absorbed this photon. What can you comment? Can you understand what is the state of atom? What is actually happening? Where the electron is?
So excitation will
Excitation will,
happen.
yeah. So of course excitation will happen, but the question is, where is the electron now and where it was? Can you guess? Now this energy is really small energy. So what you can infer? So let's say we have a chamber of H atoms, and some photons are coming with this energy and it is being absorbed. So if you obtain the spectrum, this photon will be missing from the spectrum. So this is called the absorption spectrum. So we get some lines here on a plane. If we look, this is like a missing line. So everywhere we have the brightness, except there is a place where we have darkness, because this photon is missing from the spectrum. So we call it absorption spectrum. And when the absorption will occur, when the collision is perfectly inelastic, because the energy of the photon is exactly equal to the energy need to excite the electron from the present orbit to the any other orbit. Need not to be the very next, any other orbit of high energy value. Now, if you have the value 1.89, then can you tell me the transition which is going to give this energy? So 1.89 means what? So I told you to remember the energy values. 1, 2, 3, 4, okay, 5, and this. So
Yes, sir.
we know this is 13.6, then this is the less value, 3.4, then 1.51, right? Then how much? 0.85, then 154, then 137, then 127, then 121, then 116, then 116. 1, 2, 3, 4, 5. So we had remember these values. If you so you need to just remember these values. It's pretty easy to remember. 13.6, 3.4, 1.5, 1.85, 154, 3727, 2116, or you can say 17 also, but 16 is okay. 2116, 136. So you can just read like a poem. 13.6, 3.4, 1.5, 1.85, 54, 3727, 2116, 136. So just do some mental rehearsal and you will be able to remember all these numbers. It's pretty easy to remember. And this is like the way to go forward. If you don't remember these numbers, you will struggle to solve question. So I told you that what do we remember while solving the mathematics. So this is the values which we must remember. And it's very easy to remember, in fact. And the 1.89 is a very small value. So of course, the first transition is not going to happen because this is like 10.2 we know. So this transition is not possible. So definitely the value is so small that electron cannot be in the ground state, because in the ground state, if you want to excite something, the minimum energy you need is 10.2. So if you look in, I mean, just by inspection, if you look at the values and by inspection, you can tell me what transition must have occurred with this absorption. And you can realize this is pretty easy. It's 2 to 3. So if you go from this value to this value, the transition energy is exactly 1.89. It means before the absorption, the electron must be here, and after the absorption, electron has gone here, and that is why this photon was absorbed. So this is how we understand. And of course, the energy which we need for the conservation of momentum part, that can be ignored because that is very small. So what I'm saying here is that compared to the EI is much bigger than h square upon 2m lambda square. And you can also realize that the h value, you know how small is the h, minus 34, and square means it's too small, and therefore there is no way that this can match the answer. Okay, so the whole idea is EI will always exceed this value, and therefore the the equation that we actually use to solve problem is the equivalent relation. So when we solve question, we equate this with this. That's it. And we really do not bother about the other part, this part. The reason is this is very small. Okay. So when you solve numerical, you just think this way. But when you answer the conceptual problem, then you have to understand that okay, the incoming energy should be not just equals to the energy of excitation, but slightly more than that in order to conserve the momentum as well, because you cannot violate the basic conservation principle in science. Okay. Sorry. So now the question is simple. This photon is being absorbed by the H atom chamber. It means in this sample, can we say that we have the H atom already in the first excited state? Yes or no? Hmm? Yes or no? Am I audible,
Second.
guys? So I'm saying that if in this chamber, if this photon is getting absorbed, then can we say that the atom in this chamber are already, if not all, but some atom in this chamber are already in the first excited state?
Yes, sir.
The electron is making
Yes, sir.
transition from 2 to 3, not from 1 to 3, right? Because the 2 to 3 energy value is exactly equal to 1.89. So what I am saying is, so before the transition, the electron was in the second orbit, which is the called first excited state in the language of chemistry. So this energy being absorbed signifies that the electron was already in the first excited state, and then after the absorption of this energy, it made the transition. Okay. So this is what we need to remember. Now imagine you get a question in which we have a H atom chamber, and then there are two values of photons. One with energy 1.89 is getting absorbed, and another, let me tell you, and one is 2.86 eV. Now tell me what is happening here. If this is the phenomena, if these two photons are getting absorbed 1.89 and 2.86 EV energy, what you can say about the event happening here? Tell me the event. So what we can say about the atom and its initial state and the final state?
It's someone second example.
Yeah, tell me what is happening.
Sir, some are in first excited state, and
Mhm.
they are to n is equal to 3, and then uh, and by absorbing 2.86 electron volt photons,
Hmm.
it's going to n is equal to 5 from n is equal to 2.
Correct. 2, 3. 4, 5. So we have the atoms either in any state, I don't know, but there are some sample which must be in the first excited state, and the absorption of these two photons, or you can say, see, the question can be asked like this: there are two missing spectrum, and this terminology you need to understand. So these two, there are two missing spectrum on the absorption spectrum, which are having value. So what they will mention is not the value. They will say the two values missing is lambda 1, lambda 2, which means the Sc by lambda 1. So these two values, if they mention lambda, you can convert into energy by writing Sc by lambda 1. And to solve numerical, how we write this? 1240 electron volt nanometer upon lambda in nanometer, because they generally give the answer in nanometer. So you should write like this, or you can say 12,400 eV angstrom upon lambda given in angstrom. So this calculation you need to know how to write and how to do the calculation fast. Okay. So if they mention the missing value, you can just substitute in the formula to get the energy value, and from the energy value, you should be able to figure it out that which kind of transition has occurred. So the world of atomic physics is slightly difficult and tricky because these are the intuition which you need to develop slowly, and that is why the numbers are very important. So you need to actually somehow like embed all the values, all these energy values in your brain, and not just embed. You need to also make the manipulation in your brain to understand what is possibly, I mean, going to happen here. So let's say if I replace the H atom with the lithium atom, lithium ion, okay, Li plus, then how the equation will change? So we know that lithium, hydrogen, helium, lithium is third. So you have to multiply with 9 to every number which you know from the H atom. So if you multiply with 9, you will get the answer. And so, and if it is helium, then for beryllium, then how much? 16. So these kind of manipulation you have to do mentally. And of course, no one is going to tell you this to do this, then the answer. So if you look at the JE problems, which are slightly very tricky because of this particular reason that you need to do a lot of manipulation. And if you fail to do all this manipulation, things will be really complex in this chapter. So you have to develop this the visualization that if this is being said, then how to interpret. Okay. Now, if these two photons are absorbed, so now can you tell me the possible values of wavelength in the emission spectrum? So what you see here is called the absorption spectrum. And whenever there is an absorption spectrum, the tendency of the atom is not to be in the high excited state for long time. So in almost 10 nanosecond interval, all will come down to the ground state. So this chamber is maintaining the excited atoms maybe through the temperature and all. So the emission spectrum is due to the transition back to the low energy state, and then the photons will be re-released into the you can say system. So this is due to the de-excitation process of electron. De-excitation. What we do the de-excitation process. So the first step is of course the absorption spectrum. Then you know what is going to happen, and we have realized one thing, that after the second question, let's say this is the problem number 2, this is problem number 1, and here we have 1.89 eV photon, and here we have 2 photons, as you can see. So try to understand the world of atoms and how they behave. Okay. So now case 2. In case 2, we have realized one thing, that the electron will go from where to where? 2 to 3 and 2 to 5, right? This is what we have realized.
Yes, sir.
1, 2, 3, 4. There are two transitions which is possible, 2 to 3 and 2 to 5. So we'll only see the higher one, 2 to 5. So now the electron is here. Now the time has come for de-excitation. So now when you try to draw the de-excitation, what are the possibilities? So you may go from the top to the bottom. Okay. You may go from top to the second one and then bottom. You may go from top to the third one and then further transition, or you may go like this and then not only this is not the end. So extend this line. So you know how many lines will be emitted, from the formula itself. So 5C2 will give you almost 10 answers, right?
Yes, sir.
And you can count it. It's very easy to count also by drawing the exact diagram. And this is also a good trick to learn the diagram. So then we can go from the second here to here, here to here. Then go one more step down, and this is also possible. This is possible, and then go one step down. So these are the possible transition. Count the values. I think 10 should be there. 1, 2, 3, 4, 5, 6, 7, 8, and 10. Yeah. So you can see that we have 10 possible transition, which is also done by the 5C2. And therefore you will get 10 different wavelengths. So emission spectrum will contain how many wavelengths? That's the question. So emission spectrum will contain 10 different wavelengths. Understood? So these kind of conceptual questions may be asked, that if you first the electron will absorb the energy, will go to the high energy state. But once you go to the high energy state, you are bound to come back, because you cannot stay in the high energy orbit because that's unstable configuration. Because the lower energy orbits are empty, so you cannot stay there alone. So you will come back till you get the most stable configuration. And why we are saying 10? Because we have infinite number of atoms in the chamber. So every atom will perform some hypothetical group of transition. So in total possible transition. Now, if I say the chamber is having exactly one atom, then how many transitions are possible? Maximum. So instead of chamber, if I say that, okay, let's say in one atom, the transition has occurred. It has gone from here to here. So in how many ways the transition could be possible? So if the electron will go from the fifth to the first, that's only one transition possible. Okay. So it will only undergo one of them. So if it goes the other way around, then it has to make one more here. So two possible. If it goes this way, then it can make one like this, one like this. So maximum is three possible. And if it goes this way, then it can make like this, like this. So the maximum possible is how much for single atom? It's only four. So we can go this way and you can make four different transition and four different wavelengths. You cannot go beyond that, isn't it? So what we say the answer is, with respect to the concept that okay, we have the infinite atoms and all atoms are infinite to make the transition. So in total, the possibilities is this much. Okay. So in the emission spectrum, the maximum you can get is NC2 number of transition and show the different wavelengths. So every transition will correspond to one particular wavelength. Okay, so we know this. And you can see that every transition is unique because the energy values are very different. And again, the other question which I asked that day, I'm asking again, how many visible emission in the emission spectrum, how many visible rays will be present or in the visible range? So how many emission, how many wavelengths in visible range will be present in will be present in
So 3,
emission spectrum. Just a minute, let me
n is equal to
complete
5
that.
to n is equal to 1.
Yeah. So the visual means what? N equals to 2, the Balmer series, right?
Yes, sir.
So this is the Lyman, which is the UV Lyman. So we can see that we have only one, two, three. Only 3 wavelength is arriving at 2. So there are 3 possible spectrum in the visible range. What about the UV count? Can you count the UV? Just look at the diagram, it's easy to count. So UV means how many can reach the n equals to 1. And you can see clearly. It's 4. Come on, guys. Can't see the value. 1, 2, 3, 4. So Lyman is ultraviolet, right?
Yes, sir.
So we have 4 UV rays, 3 visible rays, and how many infrared, including all
2.
like near, far. So you have to count everyone. 1, 2, 3. Infrared means anything beyond that is infrared. So everything above is all are infrared. So we say near infra, far infra. This is how we differentiate. So we have Lyman, Balmer, Paschen, Brackett,
Bracket.
Tiffin, Humphrey. Then Humphrey. We have like how many? Lyman, Balmer, Paschen, Brackett, the Tiffin, and then one more is there, Humphrey. Humphrey. But David Humphrey was that person. Anyway. So we have the near infrared, far infrared, they're very far infrared. You can just like this. So we can club into one context called infrared, and you can count the values of infrared will be 3. And we can subtract from the rest. So once you know the spectrum in the visible and the UV, and you know the total answer, this is also good as 10 minus 4 plus 3, which is 3. Okay. So these are the questions that you can face in understanding the spectrum part, like how the excitation and the excitation will create the variety of photons. So the next is very important from the point of view of JEE. For other examination, they may only ask the conceptual, but JEE may ask the mathematical details also. But you need to know. So this is called collision of atom with another particle. So of course we are not supposed to study just like anything. So we have very fixed value to study. So we have one H atom in the ground state. So try to understand the. This is the H atom in ground state. To make the calculation easy, so let's say if m is the mass of the H atom, and we are going to bombard this H atom with neutron. So now there are many benefits of neutron. It's a neutral particle. So this is neutron. So when you have a particle hitting the atom, it's called projectile. So it will carry energy, but here we don't write h, we write here half m0 square, and see the kinetic energy. The idea of taking the neutron is that the electrostatic interaction can be avoided, and so the energy in form of the electrostatic potential can be ignored. That's the whole idea of solving question with neutron. But at the same time, it will carry the momentum also, which is mv naught, or yeah, this is the way to write. So now you know that in every collision, two things must be conserved. So one is the energy, other is the momentum. So earlier we had a photon, and what we realized that in case of photon, let me go back to tell you. So although we were conserving energy and momentum both, but this value was so small compared to this value that it was as good as equating these two values. Now this thing will not be considered now in this case of collision of two particles. So now we have two particles. One is the neutron, and another is the H atom in the ground state. Okay, the concept of heat, if you remember, is based on the kinetic energy of the molecules or atoms. So the atom will have some kinetic energy, which we term as heat in the macroscopic world. But right now, what we are dealing with is the micro world, in which there is no concept of heat energy. There is no concept of dissipation, because the atom itself is called heat. So how can atom dissipate? That's impossible. So now we have the electron. We have the electron in the ground state, and it can go to any other state. So the only transition it can make is either E1 or E2 or E3 or so forth. Okay. And for that you need energy. For that you need energy. But if the energy of the neutron is exactly equal to the energy of excitation, do you think that excitation will take place? The answer is no, because if you only make the transition with the energy of the neutron, then what you will violate? Conservation of momentum. So we need to give some extra energy to the neutron apart from the transition energy. So let's say if I want to make the transition of electron for the n equals to 1 to n equals to 2, I want to make this transition. Then how much energy we must supply to the neutron? Can you guess? Should it be E1 or more than E1? That's my question.
More than even.
Definitely. So we need more than E1. Okay. So unless it is not more than E1, the transition will not occur, because if only difference and the kinetic energy are equated, then in that way you will end up violating the conservation of linear momentum. Because if something is coming in the beginning, something must be moving afterwards, because the momentum is conserved. So this you can reimagine as a collision of two particles. Now luckily the neutron mass is same as the H mass. So if the mass of neutron, if I say, let me make it a different mass, m, and yeah, this will be a nice idea if I introduce capital. So to solve such question, we have a very interesting method to make this transition possible. And this energy is called, because see, if you want to conserve momentum, which means you want to maintain the velocity of center mass, right? Isn't it? So what is the energy if the system is having neutrons? So this is like a two particles, one is small and other is capital M. These are two particles. This is moving V naught. So what is the kinetic energy in the CM frame available? If you remember the mechanics, the energy available in the CM frame is actually called useful energy, like that can be used for other purpose, right? Because we cannot take away the center mass energy or its velocity, because the collision is internal process, and the internal process cannot change the momentum part, the conservation of momentum or velocity of center of mass. So we need to look for that energy which we can get in the center mass frame. And I believe that all of you must have forgotten this. So you can remember this answer. This is very simple. The energy which is available for transition comes from here, if you remember. So the energy in the CM frame, the energy in the CM frame is this much. And what is the mu value? Mu is the reduced mass, which is product of mass upon sum. So those who don't know what is reduced mass and what is this energy in the CM frame, I will recommend to watch the center mass videos, which I hope is available on the YouTube, isn't it? Videos are available there. I think Amisal might have shared with you guys.
Yes.
Okay. So the whole concept of conservation of momentum is about the velocity of center of mass. And if the VCM is constant, it means the kinetic energy of center mass is also fixed. So the energy of the system is basically sum of two energy. One, energy of center mass of system, and two, energy energy available in the center mass frame for the given system. It means you need to see how much energy the center mass carries, and also you need to see what is the additional value that is available in the frame of center mass. The sum of two is called the total energy of system. Okay. So the total energy of system is half from V naught square minus energy of the center mass, which is the total mass, plus
Okay.
VCM square. And if you subtract, what you get is called half mu u relative whole square. So if you see the way to remember that the total energy of system minus energy of center mass is always equal to this value. So if you don't know, just remember it. Derivation is given in detail in the lecture, and I will recommend you should watch. So I think many of you have not watched, so you should watch this. So just remember. Yeah, cumulative energy. Very good. So now in collision, of atoms, this cumulative energy, or this called the Ke mu, is very important. And this is how we can going to make the justification of nature of collision. And here we again have the three types of classification. So classification of collision again we have here, but we have here three types: perfectly elastic. This is tricky one. Second is elastic, or you can say inelastic. I'm not using a perfect word, so it could be partially anything. Perfectly inelastic. So in case of atom, how this definition will occur? Because see, in case of particle or in case of the visible object or the macro world, we know the meaning of these three words. But what about the atoms? Like how we can define the collision is elastic, inelastic, or perfectly elastic? Okay. So there is a simple rule in the world of atoms, and the rule is: see, we cannot take away the energy of center mass. So we have some money left in our pocket, and the money left in our pocket is half mu u relative whole square. So this is called the free money, the free energy, if you remember. So if you consume this free energy completely, we call it perfectly inelastic because you have just eaten away the energy. So we call it inelastic. What is the perfectly elastic definition? When you do not eat this energy at all, it means the energy in the CM frame is intact. Nothing has been utilized. So we say perfectly elastic collision. And if you use the partial value of this energy, then it is in between the elastic or inelastic case. So you have to classify the types of collision based on the energy of center mass. I mean, energy of the system in the CM frame or the cumulative energy. So if the cumulative energy in the very beginning is maintained throughout, it means it is not absorbed at all. Then this is similar to the situation when the kinetic energy of the system is maintained throughout. So there is no conversion, there is no consumption into potential. So you can withdraw some correlation, but the way to understand is looking at the Ke mu, and you can always decide about. So in this case, let me tell you the mathematical way to remember: the Ke mu before is equals to Ke mu after. That's the meaning. Does it make some sense to you? What about the perfectly elastic case? So Ke mu after must be zero. And what about the in between? So Ke mu after so, this place actually. So Ke mu after is more than zero. So it's not zero, but it's less than Ke mu before. So in the case of collision with particle of atom, so atom is colliding with a particle. So like neutron is hitting the or bombarding the H atom with neutrons. So generally we bombard with the uranium with neutrons for carrying out the nuclear transmutation. But here things are different, and sorry, and we assume the collision is head-on collision because things will be easy. So we are considering. Okay. So the classification is clear to you guys. I mean, what is the meaning of classification in case of atoms? How to understand this? Now you know how to understand the classification, but the question is when this thing will happen. Okay, when this thing will happen. So like, what will be the case, a mathematical situation for perfectly elastic collision? Because our electron is in the ground state, that is for sure. And now I'm asking you guys that what will be the basic mathematical condition for collision to be perfectly elastic? Like the energy of the neutron is not taken at all, so this is maintained. And the answer is, look at this. So for perfectly elastic collision, the rule is simple. The Ke mu is less than even the first excitation energy. It means you cannot cross the first orbit. Like you cannot go even from one to two actually. So if you can't go from one to two, then definitely you cannot go from one to three and one to four, one to five, one to six. So the meaning is if the energy available in the CM frame, and then we have the other one. So if the energy in the CM frame even do not match this value, so this is called E1. I mean, so this is called E1. So if the energy available itself is not good enough to excite to the first orbit, then there is no question of second, third, and fourth. In that case, it will not be absorbed at all. So no energy will be consumed because it is of no use. No? If you can't go anywhere, then why will assume or consume? Because the rule of the electron is it will go only by consuming energy to one to the other orbit. It cannot go in between. Okay. So if the K mu is less than E1, then this is going to be perfectly rational. Nothing will be absorbed, and the neutron will just move with its own motion. It may reflect back, and how the things will be like momentum will be conserved, and that's it. So electron will remain in the ground state. That's the meaning. So what about the second case? For perfectly inelastic body. So what we can say, guys? Tell me. In this case, the K mu must be equal to one of the transitions. So either E I, where I belongs to E1 comma E2 comma E3 dot dot dot, which means anywhere. So if the energy in the CM frame is exactly equals to the one of the excitation energy, which I don't know which one, so I'm just writing in some mathematical notation. So it could be either E1 or E2 or E3 or E4 or so on. So if it is equals to one of them, then the energy will be taken away. Center mass will move with its own velocity to conserve the momentum part, and the energy in the CM frame will be consumed in excitation. So let's say we can also write as half the product of mass upon summation of mass into initial velocity v square equals to EI. And the way to understand here is the kinetic energy of a neutron, or okay, not neutron. So I'll write kinetic energy of projectile is half mv naught square. So let's symbolically write as Okay, not symbol. Just write K. Okay, all that's all. We can write it like this. So we have a question one, we have question two. So from one and two, you can say something that the kinetic energy of projectile. Just so kinetic energy of projectile. If you just segregate this part, will be equals to is small m plus capital M upon a small m into energy of excitation, and this kind of question will come. And this will be equals to 1 plus, I made a mistake, I think. Yeah, yeah, no mistake. So this is 1 plus. Oh, my bad. Capital N, this is capital N.
Yes, sir.
This is just correct. This is capital N. So the kinetic energy of projectile will be 1 plus, slightly more than the excitation value. So this formula is very useful because they will ask you that if the transition is happening is E1 or E2, then what should be the kinetic energy of the projectile? In our case, M and M are equal. So for given situation, since M is equals to M, then you can clearly see that the kinetic energy that we need for the projectile to make the perfectly inelastic collision is equal to twice of energy of excitation. Do you realize this?
Yes, sir.
If I put M equals to M, the answer is this is 2 times EI. Okay. And now it becomes a very interesting question that if the our question is neutron, so for E1, what is the kinetic energy we need for the projectile? And that's very easy to understand. Twice of first excitation energy, which is 10.2 eV, right? Do you
Yes,
realize
sir.
this?
Definitely.
Which is 20.4 eV, right? And so you can understand what you can understand. You can understand one thing that if very carefully, look at this demonstration. If the kinetic energy of neutron or the neutron, not crystal. Okay, I need to change because we are solving for neutron as projectile. So I'll mention neutron because in case of neutron, M and M are equal, so we have this answer. So if kinetic energy of neutron is less than 20.4 eV, what do we expect? Which kind of collision? It means if it is less than this value, it means the the electron won't be able to even make the first transition, and if it will not be able to make the first transition, it will remain there in the ground state. So all of the energy in the CM frame will not be consumed at all. So what kind of collision will be there? So this is the answer. Perfectly elastic. It means in our discussion, if the kinetic energy of neutron is less than 20.4 eV, the collision is going to be perfectly elastic collision. Okay, I think you guys are not able to make it right. Look at this formula.
Yes.
Okay. So see, I mean, for JE, definitely I know you need to know the derivation method. But for other examination, just remember the answer because this is famous answer. Like if the energy is less than 20.4 eV, I mean, they will ask you this question only: the H atom and the neutron. So if it is less than 20.4, then what will happen? Then in that case, what will happen? It will not be taken by the electron. So the electron will remain in the ground state, and the kinetic energy in the CM frame before and after will be same, and we call it perfectly elastic collision. So does it make some sense to you guys? Yes or no?
Yes.
Yes, sir.
So now we can go to the next discussion part. So if I tell you that okay, the incoming neutron is having energy 10 eV, what will happen? The collision will be elastic, inelastic, perfectly inelastic, or partial. What do you expect, guys? So this is,
Perfectly elastic.
yeah, this is definitely perfectly elastic. In fact, it is 20.
Perfectly elastic.
Yeah. So even if I say 20.3, 20.98, it is perfectly elastic. Okay. So in solving numerical, we know that some numbers on the second place or decimal may change slightly, but that's okay. We can equate. So the whole idea is this. The the next scenario is very interesting. So what happens if the kinetic energy of neutron neutron is so what happens if the kinetic energy of a projectile is not equals to, okay, so uh, is more than twice E1 if K is more than twice E1. Yeah. But and at the same time, so you are more than K1, but the kinetic energy of the projectile does not belongs to the set EI such that I belongs to 1, 2, like this. Yeah. So what happens if the kinetic energy is more than 2E1? So the first transition will occur for sure, but it is not equals to, okay. We should take from 2 onwards because 1 is the annual diameter. So I is neither 2 nor 3 nor 4. It means you do not match the exact value, but you are more than first value. So this is complex to understand. So I'll take some example to make this clear. So for example, let's say this one, tell you the values. So we'll take some examples. If kinetic energy of projectile is 21 eV, now you can see that it is more than 20.4, right? Isn't it? So the
Yes,
answer is
definitely.
20. If it is more than, so now we can see that uh, again, so what I said you in the very beginning, you must remember some value, else you cannot do the manipulation in atomic physics. That's a problem. So we know the first excitation energy is 10.2. What about the second one? If you remember, 1 to 3 is how much? How much, guys? Tell me. 12 point. If you subtract 1 to 3, what will you get? If you can subtract in 10.
0.85.
It is 12.09, guys. 1 to 3, not 2 to 3. And then if you go from 1 to 4, which is the third excited state, and this is up to what you need to remember. The answer is how much? 12.75. So this is the E1, this is E2, this is E3, and you must remember. Now let's make it double. So what is 2E1? 20.4. Or you can make it half also. You can just think like this. So if the Ke is this much, okay. So okay, anyway, we should make it double, that's better. So 2E2 is how much? 24.18, right? And 2E3 is how much? Tell me, guys. 25.5, 25, how much? 5. 12.75 into 2. 25.5. So now this is the values which you, again, you need to make the calculation very quickly and then you can see something. So where the answer falls, more than E1 criteria, yes or no? So you can see that it is more than 20.4, but it is less than 24.18. Now what does it mean? Where the electron can go in this case? So what is the possible transition in this case? Tell me. Am I audible, guys?
Yes, sir.
So, so I'm asking a question that if the energy given is 21 electron volt, then we are in which situation? So the electron can cross the first orbit. I mean, sorry, can go to the first excited state, the second orbit. Yes or no? See, you need to remember one thing. In case of photon, you cannot take the partial energy from photon. So it can, you either can take completely or you can reject it. In case of particle, you can take partial energy, so don't worry about it. Just like normal classical physics collision. So here, the neutron will give partial energy, and so what you can write is that here something interesting happened. So electron will make the transition from here to here and will absorb this energy, and the system will have some kinetic energy. So we can say in this case, the neutron coming with kinetic energy 21 eV, which is more than twice of the first excited state, as we know, will result into the first transition, but still some energy will be left. So what is the energy What is the energy of system in the CM frame? Can you tell me? Energy of system in the CM frame is how much? See, K mu after can be write as K mu before minus E1, isn't it? Oh, so just a minute. Yes. So we can say the loss in kinetic energy in the CM frame is equal to the E1 part. You see the energy relation we can write directly. And of course, if you want to write in the simple way, it will be difficult. So we must write in this way. So the kinetic energy after in the CM frame will be equal to the kinetic energy before in the CM frame minus what we consume, which is the E1 value. Is this clear? Yes or no?
Yes.
All right. So in the CM frame, what is the kinetic energy in the CM frame? In case of neutron, okay, there's something very interesting. So kinetic energy of the CM frame is half m by m plus m, uh, which is m only, into V square. And if you look carefully, what is this? It is exactly 1 by 2 of 1 by 2 mv naught square, right? And in this particular question that we are solving, the answer is pretty easy. It's half of the total kinetic energy. Basically, you can say K projectile by 2. So this is the nice value, and that's why if I give you K equals to 21 eV, you can say K mu is actually only 10.5. So the kinetic energy in the CM frame afterwards is equals to the before, which is 10.5, and the first is taken away 10.2. So we have only left with 0.3 eV. Okay, this is the CM frame. And what is the kinetic energy of center of mass? The K of CM is how much? So if kinetic energy of mu is K projectile by 2, so the in the center mass will have exactly same value, right? So K projectile, the total value, minus K mu before, of course. The difference of the two must be the center mass actual velocity or actual energy. 21 minus, and before is how much? Half, which is 10.5. So what is the kinetic energy of system afterwards? It means if you add the kinetic energy of atom and the neutron afterwards, then answer will be how much? Sorry. So this is the some conceptually challenging problems. Plus, so we know this was fixed value because it will never go away. Plus, okay, what we lost and what is left afterwards. So the answer is 10.8 E is the answer. It means after the collision will take place, and there is no need to do like this, but you can directly subtract the transition energy. So this answer is same as KE system before minus KE, sorry, minus E1. Yes. So 21 minus 10.2. That's it. This will be 10.8. But why I have written like this? Because they generally ask this question also. Like, tell me the answer. Like, what is the energy available in the CM frame? And these are like challenging problems. Like, if you, those who do not understand the CM frame, for them it is like next to impossible question to understand, to decipher, to decode. And if any one of you are not getting it, please do. I will recommend go and watch the Saint Thomas videos, especially the CM frame. I think which is towards the end of the lecture, right? I mean, I took it in the very last, before the variable mass system. Yes. So this was the one big discussion about the atomic collision, and you try to decode on your own. Like, you just sit at home, look at the lecture videos, today's lecture, and try to decode what I'm doing. Because probably this, I believe it's very difficult part, because as a teacher for me everything is easy, but I know that from the student perspective this part is really challenging. These are some advanced formulas, and it's almost next to impossible to remember for the first time. So you need to work a lot hard to actually grab these 6 pages, or more than that. Today's lecture is 8 9 pages. You need to work a lot to understand this. If you have some doubt at this point of time, let me know as I'll proceed next.
Hello.
Yeah, is there any doubt you guys have?
Hmm.
So, how many of you are understanding this? I mean, discussion, because this is the most challenging part for most of student lives, the atomic collision. So now we can move to the next topic. I think we're done with the Bohr's theory completely. Now the Bohr's theory, this part will complete the Bohr's part. So now we are good to go with the next part of our journey, and that's called, what is called that? X-rays. So now we are going to start a new topic. So Wilhelm Röntgen. Wilhelm. So we all know the history about it. So it was discovered accidentally, and okay, guys. So he discovered this ray, and because he was not knowing any property of it, so what he named, just like mathematics, let's call X. So before he could have understood anything, the application got very much utilized in the healthcare, like human body scanning, and like before he could do much of research, the application was widespread, and he got the Nobel Prize. So this like accidental Nobel Prize winner. So how we, okay, name some rays as by some name, gamma ray, X ray. What exactly classify these naming actually? So we have something called electromagnetic spectrum. And as per our convenience, and the historical reason. The different range of energy has been given different name actually. So in the energy level values, if we go from the the lowest energy to the highest energy, then what is the lowest energy rays? What we call the lowest energy rays are called radio waves. Okay, sorry guys. So in the entire electromagnetic spectrum, the lowest energy is called radio waves, and there is a lot of application of radio wave because it's almost like a zero energy wave, and we designed the RFID. You know what is RFID? Radio frequency interface devices. So just you should know some name. So if you know the fast tag, which is used in car or any vehicle, so basically fast tag is working on the RFID. So in their hand, what you see is the scanner, which is the RFID, and it's a low energy device, and because it is working on the wavelength of radio wave, so it's the wavelength of radio wave is up to kilometer. So it's easy to detect the or read the tag, which is attached with a magnetic tape actually, and the scanner will scan the tape, will read the data, and what they do is they update the data once the you cross the tool. So okay, it's designed like this. So this is the lowest energy devices, and there are a lot of application to RFID. You can study about RFID on net. In the energy spectrum, the moment you move away from the radio, you come to the very famous microwave. And needless to say, so microwave is nowadays converted into oven. So long time back, the microwave was actually used for the radar communication. And again, as I said, like the entire world, uh, they do the defense research in respective countries, and when the technology is old enough, they give it to civilization for their consumption. And this is what you will realize later on, that nowadays you're getting 5G. 5G is nowadays available in some part. So because the military has already moved to the, like you can say in India, the DRDO must have at least 7G or 8G technology. So they use internal. And the rule is like, I mean, there are a lot of protocols for manufacturing of equipments, and they follow certain protocol in which you cannot manufacture something which is much advanced than present technology. And across the world, we have so many standard which maintain these. There are many regulatory bodies which maintain these the protocols. If you do not, if you violate, you will be in jail. No, anyway. So the next is coming after microwave is what? The IR wave. Now see the application of IR is too much. You can see everywhere the camera, you know, the night vision cameras are using the IR technology or IR waves, so they can scan and you can see a fairly decent image even in the perfect night condition. So for us, for human eye, because we only operate in a domain called the visible domain, but IR can see something. So if we have a scanner which can see things in the night also. So for us, it's night, but for the eye, it's not night. So every human body emanates IR, infrared. So we, as an individual, are creating infrared waves already, all the time. So with a device, we can detect and we can. It's like a mapping process. So they create the pseudo picture of the mapping, and they convert into the bright picture into the visual range so that we can see, and that's what the technology does. So it's a infrared world, and applications are wide. You can see all across. So now, energy-wise, we are reaching slowly from the least energy to the infrared. So once you cross the infrared, then you can come to the visible spectrum, right? So visible is a range of energy or the frequency or the wavelength in which the human eye operate. So the limitation that we see of a spectrum, so the electromagnetic spectrum is the wide spectrum, and what we see is the tiniest part of it. Or you can, I mean, say that we can only intercept a wavelength whose values lies in certain range, and this is because of the physical limitation of the rods and cones of a retina. So in retina, we have the rods like cell or cones like cell, and the human tissue or the cells are also having some separation. So the brain will intercept those wavelengths which can be intercepted by these tiny dots in the retina. So if the wavelength is too large, the brain will be confused to interpret. So it's as good as not seeing anything. If it is too small, it will cross this barrier, which is dangerous because it can affect the other tissues because that's high energy. And only if it is some reasonable dimension, it can be intercepted and interpreted by the brain. So the entire visibility having the physical limitation in the structure of cellular level in the retina. So these dimension matter. So why we see certain things is the because of the dimension, and you will study in the wave optics about the diffraction and interference. And similarly, the human eye is like a screen on which we have a diffraction pattern of the external world images. So the brain is able to focus the image, and I was also surprised for a very long time that how brain knows that the image which it is seeing is focused and cannot be focused more. Like how you understand that the way you're looking at something is the perfect way. So what you're reading right now on this blackboard, is this you're supposed to read or it can be made better? Okay. So how brain manages this the blurriness to the contrast of any image. So brain is having the internal the intensity modulation. What it does is it tries to create a various image of varying intensity, and it arrives at the intensity which is maxima. So our brain generally stops making the correction in the focal length of eye when the intensity reaches the maximum. So at maximum intensity, it will stop. So if you try to defocus left to right, the intensity will drop and the brain understand, okay, this is the right image. So this is how we interpret, and these kind of applications are very important in the designing of the computer vision or artificial neural network. So when we have a computer image monitoring through the camera, we do the same technique. So we use the intensity maximization, which is actually done in the reverse process called the minus intensity minimization. So we draw the negative intensity graph and then we minimize this. And this is done easily by the computer using something called the gradient. So there are many, many more things about the world. So the whole idea is we are looking at a small part of the spectrum and then you move forward, you move forward, move forward. Then you go next. So after visual, you go to the somewhat more energy values, and we call it what we call ultraviolet. So UV is above the visual spectrum. So after UV, if you cross all UV energy level, where you reach? So what is more than the ultraviolet? There you reach X-ray energy. So X-ray is nothing but a part of spectrum whose energy is much more than the UV energy. And once you cross the energy value of X-ray, then we have the next energy level called gamma. And once you cross the gamma rays, the next is called. Now there are many, many more in between, but this is how we are taught in the class 9th. So we'll stick to only these names, and these are very famous names. So cosmic rays are the most powerful energy, most powerful, and they are so powerful that sometimes the cosmic energy enters the computer and it goes to the register in the computer, which is located in the microprocessor, and it changes the bit value, which is very dangerous. So once you know the bit value will change, if the one of the zero becomes one, the entire calculation will change, and all the automated devices will crash. So this is a big problem with the launch of rocket because we face a lot of cosmic rays while going in the outer space. There's a lot of difficulty with the launch of satellites, the rocket space, and even during the flying of, I mean, during the flight also, the planes. So that is why every automated system works on the concept of parity. Parity is like in a plane, we have multiple screen doing the same calculation. So we have multiple computers at the back, and they all perform the same calculation. And because of some cosmic event, if some of the bit will change, so it will try to match with these two. And if the chance that all three will be disturbed is very rare because these are very rare events. But if this will mismatch, if the value will change here, it will try to match here and here. And if it is matching, not matching with the two, if the majority wins, then the value will be reset to the majority value. And that is how they maintain the parity. Okay. So it is like if something goes wrong, they will try to ask the neighbors that is it the right value or the wrong value, and that is how they maintain. So there is a so powerful rays, it can go to the devices and change the bit. Okay. So there are many nice stories about some US election in which they, when they use the first time the computer, uh, a lady got much more votes than possible because the bit got changed, and she got exactly the actual vote counting and the computerized counting was differing in the nth power of 2. So by looking at the power of 2, they knew that it's a bit change actually, and they were able to rectify this. And in the recent Mars mission, uh, the computer which they use for the mission like this is not i10 or i5. They use the Pentium 4 because it is made of the very strong metallic body, and it can prevent the cosmic penetration up to greater extent than the today's computer, which is more vulnerable. But luckily, we have the parallel processing, and things are in control. No need to worry. So now we have the range of energy. You can see these are energy range. So the name is just some sort of the idea of the giving the name is that it is meant for certain purpose. And in terms of application, by naming it is convenient to understand that okay, what kind of work we can perform with this energy value. So as you go in the energy values wise, if energy will grow, so the frequency. So frequency will also increase like this. But it is opposite with the wavelength. So wavelength will decrease. It will grow downward actually. So wavelength increases, frequency increases upward. So the wavelength of the radio wave is in the kilometers. The moment you come to the X-ray, the lambda will be in the range of from 1 angstrom, I think 0.1 angstrom to 100 angstrom. This range of wavelength we have given the name X-ray. So lower the wavelength, high the energy. So the lower part is called the hard X-rays, and the upper part is called the soft X-rays. So during the body scanning, we use the soft X-ray because hard is very hard means harsh, and it can damage the tissue. So the human body should not be exposed to the radiation much longer because we need a very small exposure. And these exposures are meant for a fraction, tiny fraction of second. So when you go to X-ray machine, it is switched on only for fraction of second. So it flashes the light, releases the X-ray, and on the screen, which is having the negative film, which is called the X-ray film, the image is produced. Okay. And whatever is blocking the ray is of course absorbed by the bones. Tissues cannot stop the X-ray, so it penetrates because the size of the tissue and the intercellular separation is much bigger than the size of the wavelength of X-ray. So it can easily cross it and go on the other side. And this is how we get the image. That's very simple concept. So X-ray is all about the dimension. So you need to understand that when we say name a ray, we talk about the dimension actually. So what matter is the dimension. Understood? Dimension is very, very important. You need to understand how things work in the real life. And when you go to the gamma ray, the dimension will change further. Now, gamma rays are also very much effective in the industrial uses. So for like let's say if you want to kill some sort of bacteria or some germs in a like bottled, packaged objects. So we have some packaged liquid or serum or medicine or anything, maybe milk also. No, not milk, but anything more chemically, protected. So it is packaged in a bottle, and you want to, because of some reason, the air may be having some germs which may disinfect the entire chemical carry out the reaction. So these manufacturing units will pass through the gamma ray, uh, you can say, purification in kind of process. So gamma ray will be released for a fraction of a second, and it will just kill everything, whatever, because this is high energy, and this energy, as we studied, the energy will have the relation of absorption by the atoms. So these are so powerful that they destroy the one atom. So it can destroy the structure of the cell also. Okay, and as a result, Okay, so what do you think as bacteria or what do you think as a virus? Virus are nothing but the design of various atoms in a certain structure way. We call it molecule, and these molecules can create a reaction actually, okay, with the other cell, and thereby they destroy the existing the cellular structure of the human body, and that is why it is important not to let them grow. So what we need to destroy is their composition, their hybridization actually. So we break the hybridization, and this breaking of bond requires energy, high energy, and this high energy is possible with the X-rays and gamma rays, and of course cosmic rays, very powerful. So human body is affected by the cosmic rays, but luckily we are not so much affected because of the atmosphere. And second thing is the Earth's magnetic field prevents these cosmic particles. When they enter, it is mostly captured by the magnetic field of Earth, and we are prevented. So you can imagine that the human life is sustainable actually because of the very strong magnetic field which is present on the Earth. So almost every plant will have some magnetic field, and the life sustainability demands this. So the entire human body, which you think is your body, is basically a dipole. So your heart is like a dipole, and you will learn in the chapter of capacitor. I will teach you that the heart is nothing but a most complex capacitor, and it is the charging and discharging process which gives you the concept of contraction and expansion, and that is how the pumping is done. Okay. And it is happening in everywhere in your big or small intestine. The charge behavior is used to propel the food further. Okay, so this is naturally controlled charging discharging process, and of course you will learn more about in chapter of electricians. I will teach you all about the ECG, how it works exactly at cell level. So we'll study the ECG at microscopic level. So now what we are trying to learn, okay, we're trying to understand the energy of this particular spectrum. So now the question is how we came to know that this is having more energy. Okay. So now we have the Coolidge experiment. I hope you remember the name. Coolidge experiment. But before that, we go in detail of the formula and derivation and graph, because that graphs are very important in X-ray. We'll try to understand why we are studying this experiment. Okay, so if you look at the H atom, okay, before that, let me tell you the energy value. So let's talk about the energy of X-ray. So in H atom, we have the highest possible energy. So the maximum transition possible is how much? When an electron jumps from the infinity to the ground, that's the maximum possible, right? And if this will happen, the maximum energy can emit is 13.6 electron volt, right? So we cannot have energy more than that, isn't it?
Yes.
And even if I go to the beryllium, so the only multiplication factor is 16 times, and try to understand this energy with the energy of X-ray. So if let's take the X-ray value, I told you 0.1 angstrom to 100 angstrom. So let's convert into energy. 12,400 upon 0.1 EV to, I mean, I should have written otherwise, so 100 to 12,400 by 0.1 EV. Now you can imagine the energy in EV. Okay, it's 124 EV, and it can goes up to 12,400 EV. Okay, so this is too much. This is like KEV, the kilo electron volt. So now you know that X-rays will have the energy in which range? Kilo electron volt. So what about the gamma rays? If you go to gamma rays, it will become mega electron volt. And if you go to the neutrinos, and some other cosmic rays, the energy goes in the giga electron volt, G. So now you know the kilo electron volt, and these are very important questions because if you go to the examination, you'll come across question in which you have to identify which values belongs to X-ray. Even this can be a question. So you need to know that okay, the electron energy will be in the keV, the kilo electron volt. So the obvious question is, if the energy is in the keV, then typically can we get this energy by virtue of any transition in the lighter elements? Is it possible? The answer is no. In the lighter elements, you cannot have the energy in the keV. Okay. So the first of all, X-ray cannot be produced by the lighter elements in periodic table. So the next question is where it can be possible. The answer is when the transition will occur in the elements with atomic number beyond certain value. So generally, in the X-ray emission, the sample material taken in the lab is generally cobalt, iron, copper. So when you design the Coolidge experiment, then you have to take some sample or called target materials. We call target material, and what we use is cobalt, molybdenum. What else we use? Iron, copper. So we can use all this. So generally, cobalt is used in lab, like they use cobalt a lot. So these are like elements which are first of all metals because they will have the free electrons. Second thing is metallic lattice will have a well designed structure called the lattice structure, if you remember, and they will have the nice spacing. And because the metals basically having the spacing is very small, okay. So the structure of the metallic lattice, the two atoms will be so close that even X-ray can penetrate up to certain layer. So in case of metal, the X-ray can penetrate because if you, again, see, for us it's a metal which is solid, but for the X-ray, what they see the world of atom, they see like dots, and these dots are just hanging in space. And for you, it's a solid object. But how the X-ray will look at this entire metal, let's say if it is a copper or maybe iron. So if you take a block of iron, then for you it's iron, but for the X-ray it's a, like the scattered lattice in 3 dimension, of course. So we have the 3 dimensional picture, and so on. I hope you understand this 3 dimensional picture. So the whole idea is X-ray actually can go up to certain depth, but not much. So X-ray will have some the wavelength can go here, it can hit here, it can come here. We'll study later on the called the Bragg's law of X-ray diffraction, and it is the Bragg's law or the interference model which gave the concept of lattice dimension. So now today we know the spacing of atoms within the lattice because of the X-ray phenomena. So we use the interference to get this answer. Okay. So we have the Bragg's law and called the X-ray diffraction. We'll study about that also in wave optics. So these atoms are like arranged in a very, very nice repetitive geometrical pattern, and any repetitive geometrical pattern is called lattice. The lattice what comes from the geometry. Okay. The whole idea is the photon, or sorry, the photon, yeah, the X-ray can penetrate metal up to few layers. So maybe 5 atom layers or 10 atom layers, but not more than that. Okay. But what about the X-ray emission? How the X-ray is emitted? So X-ray emission. Now today we know a lot about science, so we can say the X-ray emission is the inverse process of photoelectric effect. or vice versa, because X-ray happened before. So you can say the photoelectric effect is the inverse process of X-ray. But let's study in this reverse process. Why? Because you all are aware of photoelectric effect, right? So what is
Yes.
photoelectric? What is photoelectric effect? So emission of electron using the light. That's it. In crude sense, we can say like this. So when a photon will hit the metal surface, electron will be emitted. In this process, we call photoelectric emission. So photon will hit the surface of metal, and as a result, electrons will be emitted or leaving the surface. So what is the reverse process of photoelectric effect? The reverse is electron must hit the metal, and what should come out? Radiation. So can you realize the reverse process here?
Yes.
Yes, sir. So in case of photoelectric effect, the photons hit the metal, and as a result, electrons are emitted. So it is natural to believe that the nature always maintains symmetricity. Every event will have its symmetric event in nature, and that is the most profound science available. That it is natural to expect the inverse process. So when Einstein said that energy equals to mc square, that is, if mass can be converted into energy, so what is natural to think? Can we convert energy into mass? And as a result, there was a very famous experiment in 2007. That was the LHC, the Large Hadron Collider. And what we produced was the Higgs boson, or the God particles, and so on. And this was just an attempt to do the reverse process. Like if Einstein said the energy can be converted into mass, then sorry, if the mass can be converted into energy, then why not vice versa? And that's the birth of the God particle. Basically, it's not God particle; it's called the God damn particle. But the damn is removed now. It's a more flavored name across the you can say media. So it's called God particle, because the scientists just said God damn, like just like some sort of slang in America. But this is how it name got named. But anyway. So the whole idea is we are learning some inverse process of nature, and you need to understand that I'm going to hit the metal surface with electron, and once you hit the electron with, once you hit the electron with, once you hit the metal surface with electron, the electron may lose some energy. Which energy? Kinetic energy, and that energy, or you can say a fraction of that energy, may appear as photon. But the question is, we want the answer in certain range. That's the question. So I want this photon in certain range of energy, and which is very high. So what I expect is that I need to have this value very high. The kinetic energy must be very high. Then only we can get this high value. Because anyway, whatever energy you hit with, you will get a fraction of it. So if the fraction is very high, the energy must be very high. So this energy we have to make it very high, and to for electron to have very high value of kinetic energy, we must accelerate it through a very large potential. And as we said, like we need energy in the kilo electron volt, so voltage must be in thousand of volts, isn't it? Because if you multiply this with E, what you get? Something in keV. Do you realize this?
Yes.
Every if you just move one step at a time, you can understand the entire thing written in the book. So when you study why they mention thousands of potential, you can understand the reason behind this. There is a subtle reason to believe these values. So we have to create a very large potential difference And again, you will study in the chapter of electrostatics that this is produced using the Van de Graaff generator. So we have the Van de Graaff generator which can produce very high potential. Now Van de Graaff generator is very famous thing and it is available across world in various museums. And if you touch the Van de Graaff generator, not like a generator at home in other place, it's a name actually. So the Van de Graaff generator, if you touch it, your hair stand will fly off. You might have seen some picture that you are touching a iron, I mean a steel ball. If you touch and your hair on your like head will just go like this. You might have seen somewhere this experience. Anyone has seen this experience?
Yes.
Anyway, so this is the Van de Graaff generator, and we will study about this in the chapter of electrostatics. So the whole idea is we need thousands of volt potential difference to accelerate the electron, and this electron when will accelerate while the time you will reach here, you already having the energy, the kinetic energy in the thousands of electron volt. Okay, and at the end of the journey, you have to slam the metal target. There is a slot like this, and in this slot, they put a tiny metal target. So this is the rest is like slot, a big metallic chamber, and these chambers are cooled by the cooling pipes everywhere. It's a cooling pipe. So the some what do you say, refrigerators. I mean refrigerant. Yeah. So refrigerant will enter this at very low temperature. So it is maintained at negative temperature because in the process of collision of electron with the metallic lattice, this is the target material. The electron is bound to lose energy because of the successive collision with the lattice. So if electron is arriving, so it is not necessary that electron will hit the first surface. It can hit the second surface also. It can hit the third surface. So you may reach here. So maybe you are reaching here and hitting it back. So even for electron, it is easy for them to penetrate up to certain dimension. Yes, that's true. Because the size of the electron is much smaller than the lattice separation. So electron actually can enter multiple layers of the metal. Okay. And a single electron undergoes multiple or you can say successive collision with the lattice and eventually will come to rest. Every time you slow down, what will happen? So every time you will slow down, your kinetic energy will be lost, and that energy will appear as heat light sound. So there will be some cracking sound, some light will be emitted. Light means some spark will emitted. So you may get some visible light also. And some high energy radiation, which of course you cannot see, will also leave the target. And what happens that when we design the cathode ray discharge tube experiment, then so this happened from the cathode ray experiment actually, and it was later on performed by the Coolidge as a proper thing, and we studied about the Monstrous law in this chapter. So what happened that there was a metallic plate wrapped in the some black paper, a black foil, not paper, and some radiation actually entered this black paper and get. I mean the I think there was some film. Yeah, it was some aluminum foil and there was a yeah film actually. So a film was wrapped in aluminum foil to protect from the radiation, but some radiation entered it and it created the spots in the film. So the obvious question was if something is covered and is getting affected. So they tried to figure out why this happened. So they figured out that okay, it was this was kept near in the lab near the discharge tube. So some radiation must have came out of tube which has entered this metallic foil. So it must be very powerful or very small in size. So low wavelength and high energy. And this high energy particle, photon entered this aluminum foil and entered and simply affected the the zinc plate. Generally, they take the zinc plate for this as a film to produce the scintillation and all in some experiment. And from there, the Röntgen realized the birth of something new, which is much more powerful than what they have seen before. So this was the birth story of X-ray, and we'll study about it in detail in the next lecture. And right now, I'll end the lecture here on. And okay, we'll finish this X-ray part. So X-ray is very interesting and it's very conceptual. So we'll study in detail about the mathematical relation. In fact, we will be able to understand the graph also. So you need not to mug up the graph. So if you see the graph in the book, it looks like some very random picture with some spikes drawn suddenly. But there is some logic behind everything which you see, and we'll come to that in the next lecture. Okay, thank you.
Okay, sir. Thank